Okay, recording's going. So welcome everyone to the last lecture. This is lecture 20 of Vector 101. And we're going to be continuing our discussion of 3D rotation from Monday. But before we get into that, we're actually going to revisit the affine map class that we started writing last week, just to sort of refamiliarize ourselves. And then we'll recap 3D rotation. I promised a discussion of Euler angles. They won the vote last night over axis angles, which I was a bit sad about because I think my preference is axis angles, but we'll do Euler angles. And then lastly, we're going to implement Euler angles into our affine map, and we'll be done. Reminders as always, doing the exercises is important. I think this last exercise is fun, which is creating your own affine map. And then office hours are always going to be on Saturday. Well, for now they're on Saturdays at 1 p.m., but maybe you didn't notice we actually had office hours even before the course started. So we'll probably continue to have office hours even after the course ends. They might move from Saturdays, but we'll probably continue to have them. Okay, just a short recap of what we were discussing last Thursday so that we can remember how our affine map class works. So we discussed homogeneous coordinates. And homogeneous coordinates, they allow us to write down affine transformations as matrices. And this was kind of surprising because an affine transformation in general is not a linear transformation. So why should we expect to be able to write it down as a matrix? And what we found is that we had this trick where, like, if you go up one dimension, you can actually write it down as a matrix. And it's a matrix like this. So again, this T is an affine transformation. And A here, this is like the linear part of the affine transformation, and then B is the translational component. And so we stick them into a matrix like this. So A goes here, B goes there, and then on the bottom row we have zeros, and in the bottom right corner we have a 1, and then X is here, and 1 is there. This was homogeneous coordinates. It allowed us to write down an affine transformation as a matrix. I drew out this like dreaded picture, but I'm actually just gonna show you something in Studio. Okay, and I guess we don't have to go over this again, but this was like how we arrived at the idea of homogeneous coordinates, which was that like we wanted to do some affine transformation, and here we did it in 2D. So like we took the blue thing, oops, right? So the blue square is what we started with, and we did some affine transformation to it. And the reason it's affine is because we moved it away from the origin. And then to write it as a linear transformation, or well, to write it as a matrix really, what we did is we looked up one dimension. And we noticed that if we do this linear transformation in 3D, then it kind of like mimics our affine transformation in 2D. If we look at this like slice of it here. Okay, I won't dwell on this too much, but anyway, this was our motivation for going up one dimension to write down homogeneous coordinates. And the height of this plane is 1, which is how we end up with a 1 in our homogeneous coordinates. But anyway, so this was just a recap from last week. Okay. And then like the cool thing about this is what we observed is that a C-frame is an affine transformation, and you can write it like this. So like in Roblox's C++ code, like this is what they're storing. They're storing these 12 numbers to define a C-frame. And because like this bottom row is always the same, you don't actually have to store the bottom row. But like this was A and this is B. And so that's how C-frames work. Now C-frames actually impose some extra constraints onto A, which is what we talked about on Monday. And I guess I'll mention it again today. So like in general, like this is kind of the shape of an affine transformation, but for C-frames, we have some constraints on this. Okay, so then we did all that, and then we coded our affine map class. And we started with these simple ones. This .new constructor, this was a translational affine map. Then we had the from matrix constructor, which lets us build, it lets us specify all 12 numbers in our affine map. And I think we tried multiplication, but like something went horribly wrong. And then plus or minus, I think this might have actually just been homework from last week. But some of the sort of like the easier ones that I wanted to get to that we just didn't have time for is these blue ones here. So real quick, I wanted to get to these today. And then later on, we'll talk about the rotational methods. All right, so back into Studio we go. Okay, here was our affine map. It actually looks a little bit different than last week because I fixed some of the issues we were having. Aha, this is the wrong affine map. This is the one with the new changes. This is the affine map. So we did .new last time. We did from matrix. Okay, so here was one issue we were bound to have. So basically last night I had like a big fight with metatable oop and realized that I should just never use metatable oop again. So I'm not going to explain how this is affine map works, but it does work. Yeah, it's horrible. And then I also had to go into the matrix class, and I had to change how the is matrix works. So here, this also has some jank to it. I don't want to talk about it. Yeah, if somebody like actually wants to know what the issue was and how I fixed it, I'll answer after class. But for now, we'll just go with it. Yeah. Okay. So what was actually the issue last week? Because we were like sending our parts into the void. Was that we were doing our 2C frame wrong? Uh, I think I had like these 9 numbers transposed or something. But the 2C frame works correctly now. Addition, subtraction. So we actually didn't do addition or subtraction last week. So like the I had said it was kind of going to be more effort than I wanted to do. That's because so we implement the affine map addition with matrix addition. But what happens is that bottom right corner that's supposed to be a 1 becomes a 2 because we've summed the 2 affine transformations. So all we do is we just add the affine transformations as matrices, and then we fix that bottom right corner. That's how the addition works, and the same goes for the subtraction as well. So we use the matrix subtraction to do the subtraction, but then we fix that bottom right corner. Any questions about this code that I've written offline before we write new code? Oh yeah, Bort brings up a good point. This is not the most performant way to be doing this. So like I have implemented my affine map with a matrix object. And I did this intentionally uh, because I wanted to emphasize that an affine map or inhomogeneous coordinates it, like is a matrix. So like we can just use the matrix object. But like this bottom row, that's all zeros and then a one. This is it's always going to be that. We don't actually need to be storing it. So you could just store 12 numbers, uh, and then like hand multiply or like hand write out all of the multiplies and additions instead of using the matrix class. But I think it is easiest to just use the matrix class. Yeah. Okay. If we all feel comfortable with this, then we're going to add some simple ones just to sort of flesh out our affine map and make it look a little bit closer to the C-frame API. So first, I want to do the dot x, y, and z properties of a C-frame. These just give the x, y, and z coordinates of the translation. But because our affine map is like just a matrix, I want to implement the properties as methods instead. And I did this way at the beginning for our vector class as well. So what I'm going to do is I'm going to do just affine map x. And this is going to return the x coordinate of the translational part. So that's going to be the first row, fourth column. And then pretty simple to then do y and z. So then the y coordinate of the translation is going to be the second row, fourth column, and the z component is going to be the third row, fourth column. And then all of these three together, these make up the position property. So we'll create a new vector. This is going to be the ones that we just did above. Okay. I'm probably just going to fly through the next few, so please pause me if you have any questions. But all we're doing is really just like returning things that are in the matrix. So next we're going to do the right vector. And as we can see here, the right vector, I mean, this is just the first column, or the first, I mean, not entirely the first column, but it's these three entries. And so we'll return those. And we actually do need these. I have some code that relies on us having this. So if we don't have them, then it's going to be an issue. So this is going to be the first three entries in the first column. And then the up vector, we just look at the second column. So we look at these three entries here. And then the look vector, very similar. Except with the look vector, we actually negate each of these because if you'll remember, we put into our matrix the back vector, which is the negative look. So to get the look, we have to negate this. All right. So those are just some basic properties that the C-frame has that we may as well put into our affine map. Any questions? Oh, good point. I did forget these negatives. Okay. All right. Yeah. Oh, there's actually one more that I wanted to say. So with this, a C-frame, like you can't scale a part with a C-frame, but with an affine transformation, you can. And so we might as well support this. So that's 1 point for affine map. So we're going to create a new constructor, and this new constructor is just going to be called scale, and it's going to be the amount that we want to scale along the x-axis, the y-axis, and the z-axis. And so it's going to look very similar to the identity. Okay, well, first of all, we want no translation. And then what we want to do is take our x-axis and scale it by sx. And we take our y-axis and scale it by sy. And well, I keep saying x and y, I mean the right, the up, and the back vector we want to scale by sz. I want to demonstrate what this looks like. Now, before lecture, I wrote this affine part object, which should hopefully allow us to visualize our affine maps. The caveat is that I have not tested it. I wrote this in about 10 minutes. We're going to find out right now if it works. Okay, so we're going to create some affine map, and let's make we'll use our new scale constructor. We want to scale our part, let's say 2, 3, and 4. So then create a new affine part, and we'll apply our affine map to it, and hopefully we see something happen. Oh, that was the wrong button. That's not even the script. Okay, if this doesn't work in like 30 seconds, we'll move on, but I thought it was worth a shot. Okay. Well, I don't know. Okay. Maybe I'll update you guys after lecture with this. I apologize. Okay, we made some updates to our affine map. Now let's actually talk about rotation 20 minutes into lecture. So a bit of a recap on 3D rotations. I wanted to create a sequence of visuals to support this. Didn't have time. So I'm just kind of like going to repeat the highlights from last lecture to you. So the first thing we claimed is that rotations are linear. And maybe this isn't so surprising because if rotations weren't linear, we wouldn't be talking about them in a linear algebra course. It's not hard to see that they're linear. I just didn't like make a diagram. But maybe you'll trust me that they are linear. And so if they are linear, then we can represent them with some square matrix. So let's suppose that Q is a square matrix and it represents a rotation. Well, what properties should Q have? And maybe I'll ask, does anybody remember what properties the columns of Q should have if it represents a rotation? Okay, so for example, let's say that these are our X, Y, and Z axes, and we want to rotate them this way. Well, the first important thing that we notice is that these blue vectors are still orthogonal. So the columns of Q are going to be orthogonal. And this is important so that we don't, like if they weren't orthogonal, we would be skewing our axes, and this wouldn't be a rotation. So the columns should still be orthogonal. But what's more is that they should also be unit length. So if the columns are unit length, then we also don't get any stretching. So we've like, here we've like eliminated skewing, and here we've eliminated stretching. And what this means, these two together mean that, I don't have any space for this. Well, how about this? These two together mean that Q is an orthogonal matrix. So if its columns are orthonormal, we call Q orthogonal, and its determinant is going to be either +1 or -1. Does orthonormal mean both orthogonal? Yeah, that's right. So orthonormal, yeah, orthonormal means both orthogonal and unit length. So we steal the ortho from orthogonal and the normal from normalization. Yeah, so it's kind of strange. Like for some reason we call Q an orthogonal matrix and not an orthonormal matrix. It would make more sense, in my opinion, to call it an orthonormal matrix, but this orthogonal here means two things. It means, well, it means orthogonal columns and unit length columns. Okay. I see some typing. I'm going to keep going. So, yeah, I'd like to hear it after lecture, Aiden. The last thing that we need to enforce for our 3D rotation is that the columns of Q don't change order. What I mean by this, so let's look at our picture. So this probably ought to be like X prime, Y prime, and Z prime. So like our rotation was to go from here to there. But right now we haven't ruled out the possible case where actually we take X and we move it there, and we take Y and move it there, but then we actually like flip Z around, and Z like ends up backwards, which we don't want. That of course would not be a rotation. So we want to enforce that the columns don't swap order. At least I don't know if that makes too much sense, but anyway, like the upshot of this then is that it forces the determinant to be 1. And so in sum, a rotation is a linear transformation represented by an orthogonal matrix with determinant 1. So if you have a rotation, you can represent it this way. And conversely, if you have some orthogonal matrix with determinant 1, then it describes a rotation. All right, and so here is our C-frame picture again. And this top right corner, top left corner, this was Q. So previously I said like this is sort of the general shape of some 3D affine transformation, but for a C-frame, we add some extra constraints onto it. And the constraints we add are that the rotation is an orthogonal matrix and its determinant is 1. All right, before I get into the next part of today, are there any questions? All right, then we'll keep chugging on. So now we're going to talk about Euler angles, and Euler angles is one way of defining a 3D rotation. I think I'm seeing typing, maybe not. And to understand Euler angles, first we need to understand what are called elemental rotations. So an elemental rotation is a rotation that fixes either the x-axis, the y-axis, or the z-axis. So it's just some rotation about either 3-axis. So we rotate about x, that's an elemental rotation. Rotated about y, or if you rotated about z. And then with Euler angles are a set of 3 angles that describe how to chain elemental rotations together. For example, the from Euler angles XYZ constructor. This takes in 3 angles. These are the Euler angles. We take in some amount to rotate along the x-axis, the y-axis, and the z-axis. And then we construct from this 3 elemental we construct 3 elemental rotations and then multiply them. So we take the x Euler angle and we construct some rotation about the x-axis, and then we multiply it by a rotation about the y-axis, and then we multiply it by a rotation about the z-axis. This is like almost true. I'm actually going to show you a picture that, well, it shows that I'm like, I've been lying. I'm going to show you a GIF here that I found online. This is showing, oops, the recording is not seeing it. This is showing an applying Euler angles. So first, the sphere rotates about the y-axis, and then it rotates about its local z-axis, and then around its oh, this is so sad. I actually don't even see the thing to share my. Is it that? Yes. Can you see this? Okay. Yeah, so this is an illustration of using Euler angles. So first it rotates about the y-axis, and then it rotates about its local x-axis, and then about its z-axis, I think. I'll just let it play. What is the order that this orientation is applied in? Yeah, I'm trying to think. I think it's first the y-axis going up, and then it's the x-axis, and then the z. I actually don't think that's true. I actually think it's applying a y, x, y. Maybe I should have looked closer at this before I showed it to you all. Yeah. Well, I can show you an example in Roblox. I go back into Studio. So if I take apart, can't see that. And all I do is I use the local rotation handles. So like first I can rotate it about the y-axis, or let's do the x-axis. So let's do, let's see. Okay, so we can rotate about the x-axis, and then when we apply the next rotation matrix, it actually rotates about its like local y-axis, or the up axis, or up vector. And then we rotate about its local z-axis. Yeah, there's a question in the chat, which is like, why does the order matter whether you apply X, Y, Z, or any of the other three orders? Like in general, rotations don't commute, like Aiden said, meaning well, it's exactly, I guess, what I'm trying to describe. Like in general, you can't swap the order of rotation matrices. You'll get a different result. And then Neptune's suggestion is that maybe this is due to gimbal lock. So not due to gimbal lock, but a gimbal lock is a sort of an unfortunate phenomenon that Euler angles are susceptible to, but I won't mention that today. Okay. So now how do we get these elemental rotations about the x, y, and z axes? Well, let's go back to 2D, which I'm pretty sure we discussed on Monday. So in 2D, let's say we want to rotate the x-axis. We want to rotate the x-axis to here, to this point. We want to rotate it by some angle theta. What we said was that this point is going to be cosine theta, sine theta. And then if we also wanted to rotate the y-axis by the same amount, so this is going to be, right, there's another theta there. So we also want to rotate the y-axis. Well, this is going to be cosine of theta plus pi over 2, and then sine of theta plus pi over 2. Because like the angle that this one makes with the x-axis is theta plus 90 degrees. But as it turns out, this is actually equal to something a little bit simpler, which is negative sine theta cosine theta. So then our 2D rotation matrix became, well, for the x-axis, we moved it to cosine theta sine theta. And for the y-axis, we moved it to negative sine theta cosine theta. Let me know if you have a question about this. All right, so this is how we got a 2D rotation matrix. I see there might be a question. All right, good. So if you understand this, then you like totally understand how 3D rotation or how 3D elemental rotations work. So let's do this again, but up one dimension. And what we're going to do is we're going to fix z. So we'll keep z fixed right there. Z is always going to stay at 0, 0, 1. And then we're going to rotate in the xy plane. And we're going to have a very similar picture. So we want to rotate theta radians in the xy plane. Well, this is again going to be cosine theta, sine theta, and then for the z component, we just use 0. And for the y-axis, it's going to move over here to negative sine theta, cosine theta, and then again a 0 along the z-axis. So then in sum, our x-axis moved cosine theta, sine theta 0. Our y-axis went to negative sine theta, cosine theta 0. And then our z-axis just stays put. So it stays at 0, 0, 1. And this is the elemental rotation matrix for the z-axis. So hopefully this isn't too scary. I mean, we're basically just reusing exactly what we just saw. All right, and then you can follow a similar process for rotating about the y-axis and rotating about the x-axis. I have pictures to demonstrate this, but I mean, if we feel like this is pretty straightforward, then we can skip over them. All right. If we feel comfortable with this, then I'll just move right along to all of the two other rotation matrices. So this is the one that we just looked at. And then for our x, we're going to keep x fixed at 1, 0, 0. And then we just do our 2D rotation on the y and z axes. And then for our y, we're going to keep the y-axis fixed, and then rotate the x and z axes. Okay, that's a good question. So I'm just going to show you the diagrams that I prepared. Is it not the same process for finding linear transformations? Yeah, yeah. That I guess wasn't clear. So what I'm doing is I'm saying, like, I want the x-axis to go here. So then my first column is going to be, you know, the cosine theta, sine theta 0. And then I say, well, I want my y-axis to go here. So my second column is going to be the negative sine theta, cosine theta 0. Yeah, the columns of the matrix tell us where the standard basis vectors go. Yeah. Okay, well, maybe I'll still show you the demonstration anyway. Right. So we're going to start with these x, y, and z axes. And then we're going to move these axes to the red axes. So R is going to be like some rotation matrix that we're applying to the y-axis, the z-axis, and the x-axis. And right now, well, as you can tell, we're not applying any rotation at all. So if we wanted to rotate about the z-axis, so we're going to keep RZ fixed, and then we'll increase theta. So as we increase theta, x is going to move along. It's going to twist around the z-axis towards the y-axis. And then we can also look at the coordinates of these points. So z ought to stay fixed, so it's always going to be 0, 0, 1. And then as we saw before, like in the 2D case, the x-axis is just going to be cosine theta, sine theta, and then we tack on a z because we're in 3D. And also the y-axis is going to go to negative sine theta, cosine theta, 0. And then we can do this again for the x-axis. So now we're going to keep the x-axis fixed. And if we increase theta, well, this time, if we want to rotate counterclockwise about the x-axis, then y is going to move towards z. And so its coordinates will look like this. I'm actually watching the time, and I think we should keep moving on. But then this is how you'd get the other two elemental matrices. And so for the y-axis, then you twist counterclockwise about the y-axis, and so z goes towards x. Okay. Let's add these now to our affine map. All right, so first I'm going to implement the elemental rotations, and then I'm going to combine them to do the Euler angles constructor. We want to rotate about the x-axis, and maybe this isn't like terribly informative to just watch me type up the same math that we just saw. I'm thinking maybe if we just copy and paste it over. So to rotate about the x-axis, as we saw, so we're going to keep the x-axis fixed. That's that first column. And then for the y and the z columns, we're going to do our 2D rotation matrix. And then to rotate about the y-axis, oh, well, my tabs are all out of sorts, but right, the y-axis is going to stay fixed. And then we rotate the x-axis towards, or rather, I think we rotate the z-axis towards the x-axis. And lastly, to rotate about the z-axis, oh, well, my tabs are, yeah. We're going to keep the z-axis fixed and then rotate the x-axis towards the y-axis. Do we want any further clarification on this? Oh, good. Okay, so now what we've been waiting for, which is Euler angles. So let's do the from Euler angles XYZ constructor. This is going to take in 3 angles, the rotation about the X, Y, and Z axes. And then we can just reuse what we just wrote. So we can rotate about the X, and then rotate about the Y, and then rotate about the Z. So this is the XYZ from Euler angles XYZ. And if you haven't used this, well, you probably have, and you maybe just didn't realize it, because this is actually an alias for affine map or C-frame.angles. So C-frame.angles is actually just C-frame dot from Euler angles XYZ. So there, we get a method for free. And then for whatever reason, Roblox implemented 2 versions of the Euler angles constructor. Like they did 2, even though there's 6. I'm not really sure why they even chose the 2 that they did. But they also implement YXZ. So the first one is actually going to rotate about the y. And then we rotate about the x. And then the z. So all we've done is we've swapped the order of the first two rotations. And the JMK's comment, swapping this order, actually returns different rotations. Yeah, board. It's like I don't know why there's only two. I don't know why they stopped at two. Okay, and then this one is an alias for from orientation. Or yeah. So then this one from orientation is from Euler angles y, x, z. It's strange. It's like there's 4 constructors to do 2 of the versions of this. All right, there we have it. We should probably also check that it works. So, all right, there we go. I have 2 parts here. And what are we going to do with these parts? I think this is just some old code that I was working on. So for part 1, let's use Roblox's methods. So part 1 C-frame, we'll translate it to this position, and then we'll rotate it using from Euler angles. And let's see. How about that? And then for part 2, we're going to use our affine map. So I'll put it right next to part 1. And now we want to use our affine map from Euler angles. Put in the same angles. And then at the end, we have to tack on that 2C frame method. All right, let's give that a run. Nice. All right, always good to end with working code. I think too many times we've ended with not working code. There you have it. That's the from Euler angles constructor. I have one last thing to mention. I'm going to switch back to my tablet. I just wanted to thank you all for attending. Teaching people math is like one of my favorite things, and so I really appreciate you all like lending your time and your ears so that I can teach you things. This has been a really fun course. This is the first course I've ever taught. Actually, I don't know if I ever mentioned that. So I think I learned a lot about teaching by doing this. So thank you all for just like being the guinea pigs for our first course. And Aiden and I have chatted about possibly doing another course, either from him or from myself or from the both of us. I think at some point you will probably be hearing from us in the future. And this sounds like a goodbye. It's not. You guys know where to find me. I will always be here in the Discord. Watching the Discord grow has been so great. I created it a couple years ago, October 2021, I think it was. Like I just wanted some place to talk to other people who were passionate about the same thing I was passionate about. And it's been really wonderful to see the server grow, in large part due to this course. So thank you all. And I hope that you'll also all continue to do math after this course. I mean, I think since all of you like self-selected to sit through 20 lectures, that you probably will continue to do math. But like this is really just the beginning of your journey. there's so much more, and I hope you'll keep learning. So that's it. Thank you all for coming.